Yeah, hi. Good evening, everyone. So, welcome to the second revision session of for Quiz 2. So, actually, I'm not sure. So, some background noise. Maybe you are listening. So, some event is happening in my street, so that I can avoid. Actually, so it is manageable.
No, so your audio is clear.
Okay, okay, yeah, then fine. Okay. So, I think someone have raised the hand.
No,
Okay,
sir, it's by mistake.
okay, yeah, then fine. Okay, so I hope you have covered the week 5 and 6 in the last revision session. So today we will just recap that week 7 and week 8, and also your query if you have any doubt in any topic or any like mock questions. We have also released the mock some sample questions. So I hope you have tried it, and otherwise our TA is also actually discussing some PYQs in their session. So I hope you are also doing that. And today I have also some set of questions from week 7 and week 8 from the last previous year questions. So that are actually we can use during the revise the topic. And basically we will not teach every topic in detail. So we will discuss the important area where you can need focus at the time of preparation of the quiz 2. Okay, so you can focus more what topics are important in week 7, week 8. So yeah, that's we will start today. And before starting the session, if you have any query, then you can start. You can raise the hand. So if anyone have any query, any specific query in any topic or any
Yeah,
question.
I just have a general query just to benchmark the difficulty level of the paper as compared to the mock. Will it be like approximately the same difficulty level or
So what
uh,
difficulty level you feel for the mock? It
mock
is
was
hard
okay.
or uh,
I found it okay.
okay. So let me just quickly check the questions. Yeah, so same. Actually, all these questions are just taken from previous terms QP that exam.
No, no,
So
I know
you,
that.
so you
Sorry,
will
I was
find
just
out the same difficulty level, but
okay. Yeah.
I'm not sure that same question. Okay.
No, 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 of course not. I was just trying to understand,
uh,
and sometimes like in maths too, etc., the mock and the paper were like totally the difficulty levels were like very, very different. So I was just trying to understand that's about it.
no, no, no. So you will get the same level. Okay, if you have done all the questions of your GRPA or this theory assignments, and so you will find out the similar type of questions.
All right.
Okay.
Thank you.
Yeah.
Thank you.
Okay.
Sir,
Yes.
I have a doubt in mock question number 12 and 13. Could you
Okay.
please?
12, 13. Okay.
Yeah.
Fine. So I'm sharing my screen and just quickly discuss this mock questions if anyone have a doubt. So yeah, this one. Okay, so I hope the previous all questions are covered in live session related to the week 5 and 6. So week 12 is this one. Okay. So what's your doubt in this?
Sir, I am not able to understand the question itself.
Okay, so this is a straightforward question of the topic which is discussed in week 7. That minimize lateness. Have you seen that topic?
Yes, sir, but I
So
was trying.
quickly show you that minimize lateness that is covered in week 7. So this one. Okay, here we have some activity request. Okay, and each activity request can be done in some duration. So here it is also given. Here you can see we have some jobs ID. Okay, 1 2 3 4. After that, for each jobs ID takes this 4 time to complete. Okay, so this is the time required to complete that activity, and each activity have the deadline also given. So but we have only one resource to perform this activity.
Sir, you mean to say we have to compute, means deadline for that is 6, and it takes for one job it takes 4.
So job ID 1 actually it takes 4 unit time to complete
Okay.
activity. Okay.
Um,
Job ID 2 takes 2 unit time to complete. Okay,
Oh,
but all these activities or jobs are performing on the same machine. So that means if we are performing one jobs, we cannot do at the same time another job. So we can just perform these jobs sequentially. Okay, after completion of one, then we will start the second activity.
okay.
Okay, so in this way, so I'll explain you. One second. Uh, Okay, so these are activity. So in the question statement, it is also given that some start time. Okay, so otherwise start time is not given. That we will start from the zero start time. Okay, so for the first activity. So let's if suppose we start these activity in any random order. Here some order is given. Deadline is also given. So this is the deadline given for each jobs, and if our jobs complete after this deadline, okay, if our jobs complete before the deadline, so lateness means it is not late. Okay, if our jobs complete before the given deadline or at the time of deadline, so that we will consider that jobs is completed on the time, okay, or before the time. So that means it is not late. But so we will consider that the zero lateness if our jobs is completed on the time or before that or at the same deadline time. But if our jobs complete after the deadline, so that we will calculate by the completion time minus deadline. So that will be the lateness for this active that jobs.
Okay.
Okay, so suppose if I'm taking random order here, so I'm just going through the same order like this. Okay, I'm performing this first four that activity, and that is start at zero time. It will take 4 unit time, correct? So that means this first activity is taking 4 unit time. So end time is 4, and deadline for this is 6. So that means it is completed before the deadline. So lateness for this is 0. Okay, now we start the second activity. So this is takes 2 unit time. So but it will start after this 4. So 4 plus 2, that means end time is finish time for this is 6. Now the deadline for this is 7. So it is also completed before the time. So lateness is 0. And next activity takes 1 unit time. So that means 7. Okay, so 7 deadline is 8. Still it is completed before the time. So this is the 0 again. But now next is taking 4. So 7 plus 4, it is 11. Okay. So this is 4, this is 1, this is 2, this is 4. Okay. So now it is still completed before the time. So again 0. Now next is taking 4. So 11 plus 4, sorry, 3, 14. So again, this is also completed on the time. So 14. So it is also not late. But next is given as a 2. So that means uh, 2
It's a late.
16. Okay, but time is given for 5. Okay,
Yes.
so now how much it is late? So 16 minus 5.
Yeah. 11.
So then 11. So now among all the lateness value, what is the maximum lateness value? We have 11.
11.
So this is the value for that calculation which is given in the formula. You can see we are calculating lateness for each jobs by this formula. If our that time of completion, sorry, if time of completion is greater than deadline, so we are calculating lateness by time of completion minus deadline for that activity. Okay, otherwise 0. So this calculation we are using, and after that calculating all the lateness, we are selecting the maximum lateness among all by this formula. So ml equal to max of all lateness value. And here the manager goals is to minimize the ml. So that means our goal is here to minimize this maximum value. This value we want to minimize for this problem. How we can minimize? So this is a problem of minimized lateness problem, and how we can. So we need a proper schedule here. So we performing in this given schedule, but we can arrange our jobs in this way, so we can reduce this maximized lateness value to lowest value. So what is the way to solve is, if we can arrange our jobs by the deadline increasing order, based on the deadline in increasing order. That means smallest deadline we will perform first. Okay, if we will sort our jobs in this way, and then we will start performing our jobs. So that means first we will perform this one.
Yeah,
So
6.
5, yes,
Job
6.
6.
So now again we start this. So like if we perform, so this is the first activity will complete at 2. Okay, so this is the sixth ID. I am writing ID at the lower, and the value is 2. So 2 is the end time for this. So now deadline for this will be now 0. Okay, it is completing before that. Next is smallest is 6. Okay, this 1. So that means add 4 in this. So we are getting 2 plus 4, 6 here. So this is ID 1, and the time required was 4. And still it is also completed on the time, so 0 deadline. Now next is 7. Okay, so 7 we will add 2 here, so 6 plus 2, 8.
Sir, may I ask a doubt there?
Yeah,
We are going by the earliest done, right? The deadline which is ending fast. So first one is the job required for, and that is the one we are selecting first, right?
yes, first we are sorting our jobs based on the deadline in increasing order. After that we are selecting from the smallest one, that one by one,
Okay, okay. We are arranging it in the increasing order.
increasing order. So because of that we selected this first. Okay, and this second, then this third. Okay, then we will select this 4, and this 5, and this is the 6th order. So this order we are following now
Okay,
after
okay,
sorting.
okay, okay.
Okay, so now the second activity is completed with 2. So this is 6 plus 2, 8, but now it is coming after the deadline. So what is the lateness is 8
1.
minus 7, 1. Okay, now next is this third. So this is only 1. So that means it will complete on 9. So ID is 3 and value is 1. So what is the deadline for lateness is 9 minus 8, again 1. Okay, so now next is this 4. So 9 plus 4 we will calculate this 13, and ID is 4 and the value is also 4. So lateness of this is 13 minus 12, again 1. Okay, next is 3, so 16, and this is ID 5, and let value is 3. So 16 minus 14, 2. Okay, now these are the lateness we are getting if we are following this method. Here maximum value is 2. So this is the order where we are finding out the maximum lateness, which is actually minimum among all possible order. So this is the answer for this, minimize the lateness value. So we can solve this problem. You will not find out any order, so you can reduce more than that.
Okay, means 2 will be the lateness.
2 will be the that maximum lateness, maximum lateness among all lateness.
Okay.
So here our goal is this one.
Does they ask a minimum lateness also?
So this Asna, so here the manager goal is to minimize the ML value, and ML value is maximum among all the lateness.
Okay.
Okay, so in this way we are solving this. So we will get the 2 answer for this. So 2 is there, and after that how we are solving this. So next question is based on this. So we are solving this by the always choose the job first whose deadline is earliest. Okay, so we are sorting the jobs by the deadline and we are selecting the minimum first. So
Yes.
this second is the correct answer to solve this.
Yeah, got it, sir.
Okay,
Thank you,
so
sir.
yeah. Any other question in
Sixth question, sir.
6? Okay. Okay, so consider a binary tree with 20 nodes where the number of nodes with 2 childs node is 7. The number of nodes with 1 child node will
Fifth, sir. Sorry, fifth, sir. Sorry.
this one.
Sorry. Yes, yeah.
Okay. Okay, so let G be a complete undirected graph on four vertices. So this is given as a, we have four vertices. It may be like A, B, C, D, and we have complete undirected graph. So that means we have completed undirected graph like this. So total six edges are possible for this, and having six edges with weights 3, 4, 5, 6, 7, 8. So weights have, we have 3, 4, 5, 6, 7, 8. So these six weights are also given on the sixth edge, but we don't know what are the edge that which edge actually contain this weight. So any possible graph may be the input for this problem. So this three may be coming at this AB, AC, or AD like this. Any edge, these weights can come. So all possible input graph we have to think about here. So now the question is the maximum possible total weight, okay, that a minimum weight spanning tree of G can have. So first thing, minimum weight spanning tree. So this is actually a minimum spanning tree which contain the minimum cost. Okay. So I hope all know that what is the minimum cost spanning tree. So that means all
Yes,
nodes
sir.
are connected with minimum that cost edge, total edge. So we want to figure out that. So what are the possible minimum spanning tree for any possible input graph with these weights? Okay, among all these, what is the maximum possible weight for that minimum spanning tree? So here we have to think here one we will understand step by step here. So suppose if you are solving using the Kruskal algorithm, okay, and in Kruskal algorithm you always select the edge by the weights in increasing order. So 3, 4, 5, 6, 7, 8. Okay, now we are just selecting the edge by the weights, and suppose we have this input graph A, B, C, this D. All are actually not connected by any edge. Now we will add this 3 first. So just think that 3, if this 3 is connecting with any edge, it will always select in spanning tree. Okay, if
Okay.
3 weights is connected with any edge in input graph in this, okay, it will always select in the minimum spanning tree, because this is the first edge. It is not creating the cycle. According to the Kruskal algorithm, we not select the edge if it is creating a cycle. Otherwise, we will select the edge. Okay, and suppose it is coming on this 3. So we will select this in our. So this is suppose coming on this edge. So you can take at any place. It will always select. This is the first edge. It cannot be create the cycle. Okay, now second edge. Now we will select the second edge. Still, if you are selecting second edge in this graph, it it also cannot create a cycle. You can think if 4 is coming at any edge in this input, it cannot be create cycle, because this is a simple graph. It is not, we are not using parallel edge or self loop like this. So these two edge cannot be create cycle in this graph. Okay, so that means this will also be select. So 3 and 4 will definitely select in every spanning tree. Okay, so you can take at any place. So let I'm taking here. Okay, now this is 4. But if we are selecting this 5, there is a chance maybe it create a cycle, or it may not be create a cycle. So how it is possible that suppose this 5 bits is coming on this edge. So 3, 4. If this is coming on this edge, so that means our both these 3 edge will be selected in the graph. Okay, so like this A, and this B, and this C, and this D. Okay, so these 3 edge will be selected. So 3, 4, and 5. So this is now become a spanning tree, minimum spanning tree. Now wait for this is 3 plus 4, and 3 plus 4 7, and 5 12. Okay, so this is the one possible answer for any one possible input. Okay, but can we get more than this in for any possible input graph? Yeah, so that is the possibility here. uh, with the help of 3 edge we can create a cycle in our graph. So suppose if this 5 weight edge is coming on this edge, this one, okay, this one. So now you cannot select this because 3 and 4 you have selected, and this edge is creating a cycle between this. So you cannot select this, you have to skip this, and you have to select the next greater edge cost. Okay, so that means at that time you have to skip this and you have to go to this next one, 6. Okay, at that time this will definitely select, because in this A B C only this as can be create a cycle. Now we have taken this as a 5. Okay, now there is no another possibility to create a cycle for next test. So if 6 is coming on, suppose this one, again it will not create a cycle. This one it will not create a cycle. This one it will not create a cycle if we are selecting this. So 6 will definitely select at that time. If suppose 6 is coming on this edge, so that 6 we have to select 6. Okay, so now this is minimum spanning, this is also a one minimum spanning tree for this type of input graph. If suppose we have 3 4 and 5 is creating the cycle between 3 and 4. Okay, now total weights for this minimum spanning tree is 3 plus 4 7 plus 6 13. Okay, now these two possible minimum spanning tree are there for this case. You cannot figure out any another possible minimum spanning tree for any possible input graph. So this is the only possibility. So among all these, we have the maximum, this 13. So answer for this is 13.
Got it, sir. Thank
Okay.
you, sir.
Yeah.
This one was solved in the previous session, I believe. Yeah.
Yeah. So this is belongs to the week 5 or 6. So yeah, definitely maybe solved. Okay.
So can we look at question number 11?
Okay. 11. This one, Huffman. Correct?
Yes.
Hmm. Okay. So here it is given that which of the following statement is true about Huffman code algorithms. Okay. So some common that features Huffman tree contains that this is statement. Huffman code algorithm is based on greedy approach. Yeah, this is true because every time when we are creating Huffman tree, we always select the smallest two weights, and then we create a graph like this. Okay, we always select two minimum, then we merge this into the bottom up manner. So this is a greedy approach. This is true, and that Huffman algorithm code algorithm always generate a prefix code. Yeah, this is also a true property, because what does this mean actually, prefix code? So suppose if we have character A B C D E in the Huffman that when we are generating Huffman code, and we are getting the code like this 0 1, okay, and 1 0 1. So like that 1 1 1, okay, and 1 that we can take only 1. Okay, now other is we can take like 0. 0 is not possible. Okay, so 1 that 1 1, or we can take is also not possible. 1 1 0 0 0, like this we can take this 0 0 0. So in this code you can see if we are taking any smaller code, this one, okay, so 0 1, this cannot become as a prefix in any of the other code. Okay, and if you pick this is also incorrect. Yeah, we cannot take this. So this is not a correct example, but actually that Huffman codes, when we are creating any Huffman codes, you will always get a code. That code will not be the prefix of any other codes. Okay, here this one, you can see this one is a prefix of this code. You can see this is a prefix, this is the prefix. So these codes are not valid Huffman code. Okay. So if our Huffman code contain this property, when we generate this Huffman codes using the Huffman tree, our codes are actually maintain this property. So no one code is actually the prefix of the another codes. You will not get any code that is actually a prefix of another code. So this property is called as a uh, prefix code. Okay, so generate prefix code. Here some definition confusion is there. So it is given that Huffman code algorithm always generate prefix code, but meaning of this prefix code is actually that code of one character cannot be a prefix of another code. So this property is called as a prefix code property. So this is again true. So you can just try it. You can just take any frequency of these characters and just create a Huffman tree and create the code, because you are creating the codes through that tree. Okay, like this. Okay, and like this. And each leaf node is actually contain the actual character or actual frequency, like this. These are the 5 characters. And if you are reading the code, you will always traverse from root to this leaf node. So each left is 0, right is 1. 0 1 0 1 0 1. Okay, in this way, suppose this is A, this is B, this is C, this is D, this is E. Because we are not taking any code till in between any node. We are always traversing from root to leaf node to get the complete code. So for A, the code will be 0 0 0. The path actually we will traverse from root to leaf. B code will be 0 0 1. C code will be 0 1 0. 0 1 0. And D will be so this is D. Okay, so 0 1 1. 0 1 1. And E will be 1. So in this code, you can see no code is actually a prefix of another code. You can see this 1 is not coming in the prefix of any other code. After that, any other code is also not coming in the any other codes. So because we are always traversing the complete path from root to leaf, we are not getting the path like this sort. If we are taking this type of code, so that will be that will become a prefix of any other code. But this is not the case in this. So that means our Huffman codes contain this property. It generate always prefix code. So this is also true. And another is in an optimal Huffman tree, if leaf label X is at depth smaller. Okay, so depth means from root node. Suppose if any node X is depth smaller, so like the example, and this is suppose a X. Okay, so depth for this is smaller. Then leaf label Y. Okay, so suppose Y is coming at this level. So depth for X is smaller than depth of Y. So now the frequency of X will less than equal to frequency of Y. So this condition is given. So frequency of X is less than. So this is smaller than. This is greater than. Okay. So it is not possible. Why? Because we always select the minimum frequency first. Okay. So if we are getting a shorter path, that means this X will contain the less number of digit in the code. So that is the shortest path. Smallest not shortest. This is the shortest length path actually. So that means this contain the higher frequency. Okay, because of that it is selected later in the process. Otherwise we are always selecting smallest one, then next two smallest one, like this. So and we are creating our Huffman tree bottom up manner. So the any frequency which are coming on the top side of the tree, that means that value is greater. So that is selected later in the graph. Okay, so this condition is not true. X is not lesser than frequency of Y. It is not possible. Okay, so this option is incorrect. Okay, it is clear.
Yes.
Okay. Yeah, if you have any doubt, please ask in this.
So I've sent a similar question, Hoffman question in the chat. Can you solve that?
Hmm. Hmm. Okay. So here probability is given like this 1 by 30, 1 by 30. What is this? 1 by 30, 1 by all 1 by 30,
No,
or
just three are first three are 1/30, then 2/30, 3/30.
2 by 30, and then 3 by 30, and then 5 by 30, and then 5 by 30, then 12 by 30. Okay. So what you can do here, okay, so all are actually divided by 30. Okay, so this is the one part of the 30. This is 3. Yeah, okay, so that means we can create a Huffman tree based on the above value because all are the actually divided by 30. So that means we can take this ratio in our frequency. So in this smallest one, suppose this is the A, B, C, D in the given sequence. So A, B, C, D, E, F, G, and then H. Okay. After that, you can create a Huffman tree for that. And the what is this? The average Huffman code size in bits per symbol. Okay. So 12, 13, 13, 1, 3, 5, and 5, 5, 10. Okay. So yeah, fine. So now how many total characters we have? 30. Okay, just remember this. We have total 30 characters. Now just we will create a Huffman tree for this. So we will select two minimum. Okay, so 1 and 1. Suppose we are selecting A and B. So we will create A and B like this. Okay, both have the one frequency. Now we will add this, you will get 2, sum of 2. Okay, now next is we have so we are getting the sum of this is 2. We will count this also to select next two minimum. Okay, so suppose we are selecting this two and this one, because these are, we can select these as a two minimum. You can also select this combination. Okay, any two minimum you have to select. So suppose you are selecting this with this. Okay, so this is already present in our tree, and this is the actual frequency. So we will mark this as a actual character C and with frequency 1. Now we will create as a internal node 3. Okay, now next two, so you got this as a 3. Okay, now 3 2 you can select again this. So then that means 2 also, this is D and frequency is 2. So 3 2 5. Okay, now you will select this with this 3.
Excuse me,
So
sir. Sir,
yes. Hmm.
yeah, I had a doubt in here. Like, can we do that 2 and 3 separately, like out of this tree, a next
You
new
can
tree?
do, you can do.
Yeah, but
Okay.
the problem was that here, if we do like in a different tree and then combine it, then it was giving slightly shorter, like the maximum bits required were 5 if we make two trees. But if we keep
Mhm.
going in the same tree like this, then it will be 6 bits.
Okay, so we will
So,
get the final answer that if we are getting any change or not. Okay, have you
yeah,
compared the final answer or not?
yes, sir.
Doesn't matter what you are, what type of tree you are getting. Okay, so but we are following the algorithm, we are selecting two minimum always.
Okay, sir.
Okay, so just solve this in this way, and you can also try to solve another way and check final answer what you are getting. So next you will select 3, and this is 3 is for E. Okay, E. So write it here 3. So 8. Now next this will be selected 2. Okay, this will be selected separately 5. Now both are the F and this is G. Okay, 5 5. Now this is 10. Okay, now 8 and 10 will be selected. So I am marking this. So both are actually internal nodes. So these are not the actual frequency. So 18 we are getting. After that, this 18 will be selected with this 13. 30. Okay,
So
30. This
12.
is uh, oh sorry, this is 12. Yeah. So last one was 10 or okay, this is fine.
H.
And this is H. And finally is 30. Okay, so this is the Huffman tree we have. Now if we find out the character, that code for each character, so A, B, C, D, E, F, G, H, total H. So now what is the length for A? Okay, so length for A is that 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. So this is just traverse the path. So 0, 0, 0, 0, 0, 0, 6 times 0. So 0, 0, 0, 0, 0, 0. And next B is also 0, 0, 0, 0, 0, 1. Okay, this side. And C is 0, 0, 0, 0, 1. And D is now 0, 0, 0, 1. Is this one. Okay. And E is 0, 0, 1. And F is now 1, 0. Okay. And G is 1, 1. F,
So
oh,
F is 010, no?
oh, sorry, upar I missed this. 0, 1, 0. Yeah, correct. And this is 0,
1
0, 1, 1. 0, 1, 1. And last one is 1. Okay. Now this is the length. So this is the 6. This is 5. 1, 2, 3, 4. This is also 6. Sorry. This is 6. This is 5. This is 4. This is 3. This is 3. This is also 3. And this is 1. Okay. Now for the average value, what you will do? You will also multiply by this because total character we have 30. Okay. So what you will do? You will multiply by the frequency. Now you have the this frequency. So 6 we have one time. And this B is also one time. C is also one time. Okay. D have two times. Okay. And now E have three times. And F we have five times. So multiply by 5. And then we have this G have 5 times. And H we have 12 times. And just add this. Okay. So total 6 and 6, 5, 8, 9, 15, 15, 12. Okay, what you are getting number is this. So this actually we are calculating the total number of bits. Okay, so 12, that's 17, 25, and 34, and 39,
76.
49, and 59, 64, and 76. Now 76 are total bits and total characters are 30. So just divide by this. Okay, so you will get 2 point something. 16, so 2.5, and then 333, like this. So this is the average bits per symbol we have for this. Now, if you create the Huffman tree in this in the different way, so your tree structure will become a different, but still you will get the same average.
So, but in that way, we will get just 5 bits for A. Like now we are getting 6 bits for A, no?
So it doesn't matter here. So suppose
Oh,
if your
that works.
so actually if your bits are decreasing for A, so maybe some bits will be increase in some like this H or
Yeah,
like
yes,
this.
yes, sir.
Okay,
The
so
some
some
some will
increase, yeah,
decrease
some,
and some
so that
increase.
adjustment will be happen in the another way.
Sir, can you tell me the other way? Like
So,
just for one.
so other way is possible that if suppose we are selecting this one first, okay, now we are getting two, and after that we are selecting this two and one, but we can also select this one two separately. So our structure will that tree will become change. Okay, so suppose we are selecting A and that B, and now this we are getting total 2, so 1 1. And next time instead of selecting this 2 and C, we will select the totally separate C and D. Okay, now this is 1, this is 2, and we will get 3. Okay, so in this way we can also create, because
After reconstruct the tree. After
hmm?
all.
Hello, yeah, so what we are doing, we are following the rule, we are selecting every time 2 minimum. So 2 minimum, there is a chance that you will get the two different combination for selecting 2 1. So your tree structure will become change, but you will get the different code, but overall maybe you will get the same output. So you can check this.
Okay, sir.
Okay, okay, so this is fine. You can try this. Are you getting different answer or not?
No, sir. No, sir. It's same.
Same, na?
Yes. No, I was worried just about that, if that matters.
No, no, no. Actually, this is we are following the same greedy method, so there is a possibility that code will become change if you are following the different method. But overall, bits you will get the same. Okay. So, any another question from this? Question number 15, 14 also, 13, 14.
Can we cover that question on the AVL tree?
Evil, is there any question is given?
Yeah, I think there is one.
This one. Okay. This is it. Yeah, let's discuss this. And we have discussed the complete step-by-step method in week 7. So if you know all the rotations, all these things, if you don't know, please check that live session recording. I'll create the event tree for this. Okay, so this is a long following elements is arranged given order to create an able tree. So this is actually given very long sequence. In general, we not gives this type of length of the question in for the exam. Okay, so initially we have given sometimes, but later we found that it is time taking question. So we gives if we ask this type of question, we give very small set of number for this. Okay, so maybe 2 3 rotation are required for that. But here, if we so this, I hope you know that how we create the binary search tree if we have. Okay, so that should also be clear because that is also important question. If you have given like any sequence 3, 4, 6, 1, 8, 2, 5, like this type of sequence is given, and we are asking that create a binary search tree for this given sequence. Just insert all these elements in the given sequence. So how we will create a binary search tree for this sequence? So first thing you should know this very well. Then we will check the this AVL tree creation. So how we create the binary search tree? So we will insert the node one by one. So like we have the empty binary search tree. We will insert this three first. So this will become a root. Okay. In this process, binary search process, we will not apply any rotations. We will simply insert the nodes because we are creating the binary search tree, not AVL tree. So now next is 4. So when we are inserting any node, we will always start comparison from the root node. Okay, and we will find out the empty position to insert, and then we will insert. Okay, so now start comparison from the root node. So 4 is greater than 3. So greater means it should be come right side on this. Now right side is empty, no node is there. So that means this is the empty place. Just insert here 4. Okay, now when we are inserting 6, so start comparison from root node. Don't directly insert at any position. Okay, this is the wrong method. Don't try to insert it directly. Okay, just you are looking just 6 and you have seen that this is greater than 4, insert it here. Always start process from root node comparison. So 6 is greater than 3, then move to the right side. But right side again we have one node. Okay, so then we will start we will compare again. So 6 is now greater than 4. Now this should be the on the right of 4. So right is now empty, add here. Okay, now 1 is smaller than 3 root node. Okay, now left is empty, so insert here. Okay, now 8. So 8 is greater than 3. Yes, move to the right. Right again node is there. So 8 is greater than 4. Move to the right. Again 6 node is there. 8 is greater than 6. So move to the right. No node is there. Okay, so insert here. Now 2. So 2 is smaller than 3. So move to the left. Now greater than 1. Okay, so just this is the empty place here. So insert here. Now 5 you can see greater than 3, move to the right. Greater than 4, move to the right. Now smaller than 6, move to the left. So this is empty place. Now 5. Okay, so sometimes this type of question is also asked that some sequence is given and create the binary search tree, and what are the node at the lowest this depth, actually maximum depth actually from the root. Okay, so maximum depth means this is the what is the depth. So if suppose this is the root node, so depth for this is only suppose this is at a 0 depth, so 1 then 2, this is the depth 2, and for this is 0 1 2 3, and this is also 3. Okay, so which nodes are coming on the maximum depth? So we can see that 5 and 8 are coming at the maximum depth in this. Yeah, someone raised the hand.
Sir, it is AVL tree.
No, it is binary search.
AVL tree.
Binary search tree.
We have to make AVL tree.
No, I am not solving this question. I am giving this as a first thing you should know. After that, we can solve this if this part is clear. Okay, binary search insertion is clear, then we can solve this AVL tree. So this is also one important type of questions for exam. Okay, so also just practice on this binary search tree. Now comes to the AVL tree. So in AVL tree we also follow the same rule of insertion, binary search insertion. Okay, in what way we are creating this? We will again insert the node in the same way, but after every rotation we check the balance, and if our balance is not correct, then we apply the rotation. So this is very big topic, AVL tree. So we have discussed in this Week-7 all rotation type. I'll not repeat all the things because it will take maybe 1.5 hours approx. So I am just solving this. Okay, regarding the rotation type and things, you can watch the Week-7 live session. So now here 36. Okay, so I am just inserting one by one. So 36. In AVL tree, you know that we after every insertion we calculate the balance factor for each node, and balance factor is calculated by height, left subtree height minus right subtree height from that node. Okay, and the absolute value for this difference. So now this is the 36 inserted at the root node initially, and this is a single node. So height we will consider as a 0. So no left, so no left subtree, no right subtree. So height of left subtree is 0, right subtree is 0. So 0 minus 0, 0. So balance factor will become 0. So that I am writing this balance factor definition. This is absolute value of a height of left subtree minus height of right subtree. So this is the balance factor definition, and we calculate this balance factor for each node after every insertion. So now next step is 40. So we will insert 40 in this. So 36, 40 is greater than this. So 40 will insert on the right. But after this insertion, we will calculate the balance factor. So you can see from this 40 node, no left subtree, no right subtree. This is leaf node. So 0 minus 0, 0. Balance factor will become 0 for this. Now for 36, no left subtree. That means height is 0. Right subtree, you have one that you have this part only with. So this will consider as a one height. Okay, single node we can consider as a one height. So 0 minus 1. So that is absolute value is 1. So balance factor for this is 1. So according to the balance rule, if your this balance factor difference is coming less than equal to 1, so this is fine. No need for any rotation for this. We will consider as a balance. But if we are getting more than 1, so that means our we will consider that our tree is not balanced. We will rotate the tree to make balance. So in this case, this is okay. Now 32. So in next step, 32 will be inserted here. So 36, 40, and 32. Okay, now you can see no left, no right, leaf node, 0 balance factor, 0 balance factor for this also. And left subtree is 1 height, right subtree is 1 height. So 1 minus 1, 0. So again, this is also correct balance. Now 18. So 18 will be insert 36, 32, and 40, and 18. So 18 will be insert here. Okay, so 18 is smaller than 36, is smaller than 32, so it will insert here. Now balance factor for leaf node is 0, 0. For 32, so left height is 1, right height is 0. So 1 minus 0, 1. Now for 36, left height is 2. Okay, so if you see this subtree, the height of this subtree is 2, and right right subtree height is 1. So 2 minus 1 is 1. So again, you can see all balance factor are smaller than or equal to 1. So this is again fine. So now 72. So 36, 32, and 18. And 72 is greater than 36, okay, greater than 40, then it will insert here. So again, you can see 0, 0. Now the balance factor for this is 1 minus 0, 1. This is 0 minus 1, absolute value is 1. Now 36, 2 height on the left, 2 height on the right. 2 minus 2, 0. This is also balanced. So till 72, there is no unbalanced things. Now then 5. Okay. So 36, 32, 18. Okay. 40, 72. Now 5 will be insert here. So 5 is smaller than 36, smaller than 32, smaller than 18. It will insert here. Now balance factor for this is 0, this is 0. And for 18, 1 minus 0, 1. Okay. Now 32, you can see left height is 2, right height is 0. So 2 minus 0, 2. Okay. Now this is 0 minus 1, so 1. And 36, 3 minus 2, so 1. Now you can see we are getting valence factor more than 1 in this part, this node. Okay, so one second. So what we will do, we will this part actually when we are getting this 32 balance factor, we need rotation here. So which type of rotation we will apply here? So we have seen that we have 4 type of rotation. So that is one L, 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 R, 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 L. Okay. So what type of this condition is? So this is now the balance factor 2. Which side of this node have the higher height actually? Okay. So left side. That means move to the left child node. And from left child node, which side height is more? So again left. Okay. Now you can see L we are getting this condition. So this is this case, first case, left rotation. In this case, we apply the rotation on this node as a pivot, and we just pull this onto the clockwise. Okay. So we apply the clockwise rotation from this position, and we will get this after rotation. So 18 and 32 will shift here, and this 5 will shift up, and 40, and then 70. Sorry, this is 72. Yeah. Okay. After you can see rotation, now our tree become a balance. So 0 this, 0 this, 0 this, and 1 minus 1 0, and 0 minus 1 1, and maximum height for this part is 2, and this is also 2 minus 2 0. Okay. So in this way you can apply the rotations after every insertion. So I hope you can try this. Okay, so 35, then you can insert one by one and apply the rotation. So can you try
Sir,
this?
can you please explain how you got the level 2 on the left hand side?
This one?
Yes, sir.
So this is the condition. How we are getting this 2 value? So we are checking what is the left subtree height of this 32. So left subtree height of this tree is 2. Okay. And right
Okay.
subtree height is 0. No part is connected on the right. So 2 minus 0, this is the balance factor 2 we are getting.
Okay.
If we are getting balance factor on any node 2 or greater than 1, so we will apply the rotation on that. So, but we have to figure out that what type of rotation we need to apply. So I'll request to you, if you don't know this part, rotations, what type of rotation, please watch the week 7 that live session, open session. Okay, because this is very detailed topics. We have discussed all these things in detail, and we have also take some example after that. So you will get the idea how we are applying these rotations. Okay, so that part should be clear. Then you can solve this. After applying all the rotation, finally you will get a one balanced vernissage tree. So because of that, I said that this is very long question where all many number of elements are there to insert. But in general, we not gives this type of numbers in the exam now. Okay,
Sir,
You
the values are copied twice. Actually, the list is still 34 only.
oh, okay, okay. Then we can solve this now. 34, no? Okay, okay. Okay, so we have solved this 5 now. So okay, we can move. So we have now 35. So we will insert new node in this updated. Okay, so 30. We will make this as it again. So this is 18, and this is 32. This is 5. This is 40. This is 72. So 35, where 35 will insert. So 35 is smaller than 36, greater than 18. Move to the right, greater than 32. So 35 will come here. Okay. Now check the balance factor. So all leaf are 0. 0 minus 0. Okay, 0. Now balance factor for 32 is left subtree height 0, right subtree height is 1. So 0 minus 1, 1. And for 40 also 0 minus 1, 1. For 18, left subtree height is 1. We are first thing, for height we are not creating the nodes. Okay, we are creating the longest path from root node to leaf node, maximum path among all the paths. Suppose we have node like this. Okay, so what is the height for this node? Okay, suppose this is x. So what is the height for this complete tree? So how we will calculate this? So we will find out that if we have single node, we are considering that we have single node, height is 1. Okay, so what is the path? We will check every path from root to leaf, and we will figure out that number of nodes in the path. So in this path, you can see we are getting 2. Okay, in the another one, this path we are getting 3, and in this path we are getting 4. So among all these paths from root to leaf, which one is the maximum path contain maximum number of nodes contain? So this is 4. So overall height of this tree will be 4. Okay, so do not confuse about this. We are not counting the number of nodes. We are finding out the path actually, maximum length path. And in path, we are finding out the number of nodes in that path. So in the subtree. So here for 18, you can see this part, only one node is there, one height. In the second side, you can see only one path from 32 to 35. This one path is there, so 2 nodes are there, so height is 2. So 1 minus 2, 1. For 36, so 36 is max. So here you can see, so we have two paths, 36 to 5 and 36 to 35. So which one has the longest? So you can see 36 to 35, 4. Okay, height is okay. So from this one, okay, we will check on this. So from 18, so this is the longest, 3 height, and from this part, so we have 2 height. So 3 minus 2, 1. So this is again balanced because we are getting the all less than 2. So next value is 34. So we will insert 34 in this. So again we are creating 36, 18, 5 and 40, 72, 32, 35. Okay, 34 is smaller than 36, greater than 18, greater than 32 and smaller than 35. So 34 will insert here. Okay, so now you can see balance factor for 0, 0, 0. Now for 35, 1 minus 0, 1. For 32, 0 left. Okay, left is 0, but right is 2. 2 height. So 0 minus 2, 2. And for 14, 0 minus 1, 1. And for 18, 1 minus 3. So again 2. And for 36, so 1, 2, 3, 4. 4 minus 2. So again 2. So in this case, if you are getting this balance factor more than 1 on many nodes, so always solve only the lower one first. So this one, this part you need to solve or rotate. Ever one will automatically reduce after making this balance. So this part, so this part is actually we will apply. So what type of condition this is? So which side height is more from 32 right side? At which side height is more from the child of this 32 right child left? Okay, so this is L. So this is RL case. And in this case, we apply two rotations. So first rotation apply on this child node. This is clockwise. And after that, we will apply the second rotation on this node. Okay, that is anti-clockwise. So in this way, we will get the updated tree like this. So 36, 18, and 5. And after that, so after first rotation, okay, so this 32 will remain same position, and now we will rotate this part as a clockwise. So 34 will come here, and 35 will move to right. Okay, now this will remain same, 40 and 72. Okay, after that, next rotation we will apply here. So this is actually a anti-clockwise from this position. We will rotate this side. So next part updated will be 18, 40, 72, and this side 5, and now this side 34 will come here, and 32 will shift here, and 35. Okay, so after this rotation, you can see balance factor now 0, 0, 0, 0, and this 34 0, or that 1 minus 1 0. For 18, 1 minus 2 1, 40 0 minus 1 1, 36 3 minus 2 1. So all are now reduced. So this is the final AVL tree we have for this question. So what is asked actually? Which of the following nodes would be leaf nodes of the T? So you can see in this 5, 32, 35, 72. So we will select from these options. So now 5 is coming, 32 is coming. Okay, the deadline is over. So 5, 32, and remaining are 35 and 72. So 35 and 72. So these are the options 5, 32, 35, 72. These are the coming on the leaf node. Okay. So this is AVL tree. Okay. So any query in this? Regarding the rotations, so you have to check that live session recording. So that will take time.
Sir, I have a query. Sir, when we insert into a balanced search tree, the algorithm is given that if, let's say, a value is less than the root value, then self.left.insert and self.left.rebalance. So we have to only rebalance the left subtree, not the root subtree also.
No, you are just talking about any implementation.
Yes, sir.
Right? So I'm not sure what that implementation is actually, but what happened actually if we are getting so suppose we are inserting in every implementation, first step is to insert the node according to the binary search. So after insertion, one second, I'm getting one call. Yeah, sorry for interrupt actually. Okay, so what we were discussing. So yeah, regarding this insertion, after insertion, we at the time of same insertion method, so we also check the that balance factor. Okay,
Yes, sir.
so suppose we are inserting this node here, so we check the balance factor for above node. So like this, we will check balance factor, and then we will check the balance factor for this. At any time we are getting the balance factor more than one, so same time we will apply the rotation on that. Okay, we will not check the remaining part for the rotation. Also, we will not check this part. Okay, when we are inserting, we will just traverse this path. At any point we are getting more than one, we will apply the rotation.
No,
And
sir. My doubt is that in the slides, the algorithm is given like if value is left is less than root dot value, then self dot left dot insert and self dot left dot rebalance. It's self dot left dot rebalance and not self dot rebalance.
so I'm not actually getting the exact implementation, but because what is the definition of that balance and rebalance, all this which you are saying right now. So just give me a minute. I'm opening the slides now. Okay. So just give me a minute. You are talking from the lecture slide, correct?
Yes, sir.
So Week-7, you are talking, and that is AVL tree, balance search tree. Okay, this one.
Yes, sir.
Huh. So actually here also the complete code, I think it is not given as a complete code.
No, sir.
Some hint is given for the balance. So which part you are talking now? Just tell me.
So
Yeah.
go more down, sir. I think the insert part. No, this is the more down, more down. Yes, sir, this part. If v is less than self dot value.
So this is the binary search insertion only.
So it is given that you have to rebalance the left subtree.
1 second. So what happening actually? This is a recursive methods.
Yes,
Okay,
sir.
this is a recursive method. First thing, our value. This is the inserted value which we are inserting. If this value is less than to the self dot current value, suppose we are traversing from the root, okay, and we are getting this condition. So that means we will move to the left side.
Yes, sir.
Correct.
Yes,
so we are just moving to the left side, and we are calling the same insert function on the left side. So this is again a recursive call, and sorry, we will check. So we will check this again, and we will. So this is just a binary search method. If our value is actual same, we will not insert again. If our value is less than, we will move to the left side, and then we are again performing this operation. After completion of this insertion operation, so where from we are starting that, we will check this left rebalance, self dot left rebalance. So what is the definition of left rebalance? This part. So what is the meaning of this in this algorithm? Actually, if we are inserting like this, so we have like 10 or 1 2 3 4 5, this type of sequence, and suppose we are inserting 1, this will become a root. Okay, same time we will check the balance factor on this. But again, suppose we are inserting 2, so 2 will insert. So first thing, we are comparing from this node. Okay, and then we will insert here 2.
Yes, sir.
So every recursive call, after inserting, we have the next step, rebalancing. Okay.
Yes, sir.
So that means what balancing is doing. Rebalancing is just checking the balance factor for this node. Okay.
So what if we insert 3?
So insert 3 will insert here again. Okay, so 3 here.
So then rebalance will have to occur at root node 1. But sir, in the code there is no rebalance of root. It's only rebalance of right or left. So how will it reach 1?
No, this is a recursive call. You have to understand this. You have to understanding this. First, in the first step, you are moving to the right.
Yes.
Okay. Then this is again new call. Now in the first call, again the value is greater, you will move to the right. Okay.
Yes.
Now after that, suppose this is inserted here. So then that rebalancing step will perform from here, this point. Okay, so that means first rebalancing operation will perform on this 3 node. So
Yes, sir.
rebalancing operation is will check that height of this node, that balance factor of this node is actually a greater than 2 or not.
Yes.
Okay, if not, that means we will call back to the previous part, and again the next step is rebalancing at this point.
Hmm.
So we will check the balance factor for this node. Okay, if this is balance factor is less than 1, we will skip this, and again we will move back, and the next step after the call is rebalance. So suppose at this point we are getting balance factor 2, so our algorithm will apply the rotation at this part.
Sir, are you saying that there is a root node which is above 1 also?
No, we will always start insertion from the root node, no?
So, but if you follow the code,
Sorry,
let's say we have to insert-
sorry, I'm interrupting, but is this needed for the exam? Because this is an sorry.
Huh. So, but this is one doubt. I'll clarify this. First thing, you are following some code. Have you tried to implement that code or not?
Yes, sir.
Have you write the complete implementation, or you are just going through theoretically?
I have written a complete implementation, but not of the code that is provided. I've written my own implementation.
That is working or not?
That is working.
So if that is working, so definitely you should know how this algorithm is working. So in this implementation, this is the first step for the condition. Okay, this is the first call. First, we are moving to the left or right. This for here right, and this side left. That this is the right and this is the left part. This is the recursive call, same. But if sometimes if we have completed this, okay, and we have inserted, so our node will be inserted by this condition. Okay, if at any time our this condition is any we have inserted the node, so at that time we will return back to the second step, this one. Okay,
Yes, sir.
second step. So this is actually checking the rebalance from the current node.
So my point is that when you are inserting and the root node is 1, there is no call to rebalance 1. There is always a call to rebalance the right node of 1, which is 2, and then the call to rebalance the right node of 2, which is 3. But it never bounces back up to 1. It only bounces back up to 2.
Okay, so this is also depends on the implementations. No, so which part actually we are checking. So let me once again check this. So you are saying this. Okay, so v is less than self dot value. So okay, is that this value? And first we have to check this rebalance. Any pair this rebalance is given? What is this rebalance?
No, sir, no rebalance is given, but left and right rotate are given.
So that how we can figure out the complete working of this. Okay, so
just to interrupt again, I mean, we seem to be spending too much time on this.
So my one suggestion is when you are just talking to this implementation, we have also write the complete implementation related to this in our notes actually. Okay, so week 7, this week 7. Okay, and that balance AVL tree, and you can see this is implementation is very similar to that. Just see this implementation how this is working. Okay, so you can see this call left insert then rebalance.
So where
Here
is
rebalance method is also given. Okay, now you can think that how it is actually working. Just go through for one input and just check. Otherwise, yeah, this is correct. We will discuss this. Maybe you could ask actually in the previous session, in the week 7 is discussed. Otherwise, we will discuss it next week. Okay.
Where is this code given, sir? Where is this code given?
It is given in the notes in the portal. You can see inside the supplementary content.
Okay, sir.
Okay, in this GitHub notes.
Okay, sir.
Okay, so this implementation is given, and you can see the complete part how this is working. Okay. Okay. Any other question in the mock? Any query? Anyone? No query. Okay. So if there is no query from the mock, then
Can we do this recursion thing once? I mean, we have that increasing concept, same amount of work and decreasing amount of work, right?
that is actually okay. We will discuss this.
Sir,
And
yeah.
uh-huh.
No, I was just thinking that from the week 7 and 8, whatever is important, if you can just drive from your end only, that what are the topic important, if we can just revise.
Okay. So yeah, this we will also discuss this complexity thing. Okay, if any recurrence relation is given, we will discuss. Otherwise, we have one set of the questions. So that this is also a set of quiz questions. Now it is arranged in the week wise. So week 7 and week 8. So what are the important things I'll discuss from week 7. So week 7, first things you should know the proper creation of the binary search tree. So that means basic property I hope you have done in week 6. So the basic property about the binary search tree height or maximum number of nodes or minimum number of nodes, this type of calculation formula, all these things. Otherwise, some questions. So that means this question you can see. This is a binary search tree, okay, and here we are asking that what is the predecessor node in the terms of value of node M. Okay, so this M node is given any place, yeah, this one. Okay, so this is some value, but it is indicated by M. But this is a binary search tree. Okay, so BST, and binary search tree, you know that this is ordered. Now predecessor nodes is asking in terms of value. So that means what is the just previous value of this M in terms of value. Okay, so suppose if we have the value like if we arrange all the value in sorted order, so 1 2 3 4 5 6 like this, and suppose this M is representing through this 6, so previous value is this 5. Okay, so how we can figure out this from this tree actually. Okay, predecessor node, and successor node is called as a just next value in the sorted order in this binary search tree. So in terms of value we are talking about, so in this way how we can solve this. So to solve this, you should know the traversal. At least you should know the traversal of the tree. And we have discussed this traversal in order traversal. So this is the main traversal for the BST, and it provides a sorted sequence. Okay, in the increasing order, sorted sequence. And you know that how we apply this in order traversal on the tree. So we have discussed this in week 7 also. So this is 3 steps algorithm. So that means 2 recursive call and 1 simple print statement. So that is in order traversal means left call first. Okay, so first we will call to the left child, then print node, and the right recursive call. So this is left recursive call, print step, and right recursive call. So these 3 steps we will perform from the root node. Okay, so this 3 recursive call you can see implementation also we have given in the notes, but we can directly apply on the graph, tree. So LPR, and if you know the how recursive algorithm works, so that means first this is the first step, this is a left recursive call. So that means we will move to the left child and we will apply the same 3 steps. So in this way, this we will move to the this side LPR, and again we will step the first step of this. So again this is the left, so LPR, this is the left recursive call. Okay, now this LPR. Okay, now this is left recursive call, and we have reached at the base case. That means there is no left child here. Okay, if no left child, so that means no need to do anything. We will move to the next second step for this P. Okay, so now we are at H node. So this step will print the H node first. Okay, so this means this is the smallest value in the binary search tree. And you should also know binary search, in the binary search tree, smallest value will always come at the leftmost child, and maximum value will always come on the rightmost child. Okay, because of this order, left child is smaller and right child is greater to the parent. So in this way, now this is the smallest value H, and after that no right child, this third step. All 3 steps completed. Now we will move back to the call, Now this L part is completed. Okay. Now second step will perform P. So D will be print. So D is the next smallest element. So again, this is the right recursive call. So right means move to the right. So LPR. So this is the recursive call. Now this is the first call. First step L, move to the left. So LPR. Now this is the left, no left. So move to the second step P, print O. O. Okay, and right recursive call. No right for this. So all three steps are completed. Now move back and second step P, print this I. Okay, and right call. This is the call. So L, P, R, all three steps. So first step empty, print this node P, and no right. All three completed. Now move back. All three completed. Now move back. All three completed. Move onto the top above. So now from this print node. Okay, so B, and move right. This one. So L, P, R. Now first step left. So this one. Okay, left. So J. Okay, now J and no right, all completed. Now print this E, and after solving in this way one or two times, you will get the flow of actually traversing. So P, then right. So L, P, R. So this is the first, no left, and then print K, and all are completed. Now move back to here and then move here this side. So this left part is now traverse in this in order traversal. Now print this node A. Okay, and move to the right. So LPR, and from this side move to this side. So LPR, and then move this LPR. Okay, now no left, print this L. Okay, now completed, print this F. Now this completed, now print this C, and from this side come this side. Okay, so this M, and then G will be printed, and this N will be printed. So now you can see we are getting this order of the in order traversal, and this order actually represents the increasing order of the values. Okay, so if we are asking predecessor of M, so predecessor of M means that the just previous value is C. Okay, so C will be the answer for this question. So you should know first thing regarding the binary search, you should know how to create the binary search tree. So that we have discussed in the previous examples. So if you have given one some sequence, you should know how create the binary search tree. And if you have the binary search tree, then you should know how we traverse the binary search tree. Okay, so this is in order method. Same we have pre-order and post-order method also. Okay, so in pre-order, we have discussed this thing also in detail. We always take this print step at the first. Okay, so that means P, L, R. So these are the recursive steps. So this is the print step, this left recursive call, right recursive call. Just follow these steps from the root and you will get a pre-order traversal. And post-order traversal, just move this print to and at the end. So left, right, and print. Okay, so now these are the recursive call, first two steps, and this is the print statement. So just follow these three steps recursively from the root, you will get a post-order traversal. Okay, the identification is also sometimes order is given. You maybe you will get the question is that create the binary search tree for that. Okay.
So one doubt. When nothing is told, then we have to follow the in order traversal, right?
So this is depends on the question. Here we are asking that predecessor value. So predecessor means we are just talking about some order. We have given some value and what is the just previous value. And suppose if it is a successor value. So successor is just a next value in the terms of
in the mock question number 14, there we have to do the in order traversal.
Okay, mock we have to check. 14? No.
No, sorry, sir. Actually, that is a DV question, but leave it. I mean, but it is actually related. I think there we have to do the in order traversal, if I'm not wrong.
Yeah. So in binary search tree, this in order traversal actually provide the sorted sequence. Just remember this. Okay. So it will be help. It will create a help to solve this some problems. So suppose if any order is asking that what is the next greater value, what is the next smaller value for this node.
The insertion order, we should follow the in order traversal if nothing is told.
Not insertion. We cannot say that this is the insertion order. Okay. Insertion order may be anything. So we cannot say that this is the insertion order. In order, traversal just read the element in sorted order in binary search tree. Okay, smallest one and largest in the last.
Okay.
Okay, so this is not
Sir.
a inserted order. That yes.
Sir, just can you apply that post order on that? Means, can you write that the
Okay.
first 2-3 letters?
So I am taking one
after
smaller. I am taking one smaller tree. Okay.
No, no, sir. Of that question only. Of that question only, you tell. I will get that in that. Of that last question you are solving from the pre-order.
So I am giving one example to you. You can try this. Okay. So like B, suppose C and D, F, G. Okay. So I am applying the pre-order traversal for this. This is one. Suppose this is a binary search tree, and we are applying. So pre-order traversal means PLR. Okay. So this is the first step. Print. So print the current node. So A will be print first. Then left recursive call. Move to the left. PLR. Okay. Now print is the first step. So B will be print. Okay. Now left recursive call. Move to the left. So PLR. Okay. So print this node. Okay. So this is D. So D will be print. Okay. Now no left, no right. All completed. Move back. And now right step. Okay. So right step, just move this side and PLR. So this E will be printed. So now P is done and no left, no right, move back, all done, move back. Now move to the right side. So this side PLR. So first step is actually print. When we are moving to the any call, we will print that node first. Okay, so C, left recursive call, move this side. So PLR. So print this F will print. Okay, left, right, no left. Okay, so move R, PLR, print G. So we are getting this order. This is called as a pre-order. Okay. So this will not be in any proper order. Okay. Here this will not be in increasing order. This will not be in decreasing order. So you will get some different types of order, but in order is actually provide the sorted order for binary search tree. But this time there is one identification that the first node will always be the root node.
Yes.
Okay. But you cannot identify the root node if in order is given to you. Okay. In order traversal, the root node will come in between. So you cannot figure out that which element is a root node. But in pre-order, always root node will come at the first place. And in post order, the root node will always come on the last place. So regarding the post order traversal, so suppose the same tree A, B, C, D, E, and then F, then G. Okay. So post order means L, left recursive call, right recursive call, and then print. Okay. So this print is actually moves. In order, it comes in between. Pre-order, it comes before, and post order, it comes at the last. So that LRP. Okay, so first is left recursive call, move this side. LRP. Okay, left recursive call, move this side. LRP. Okay, so now no left, no right, print. So D will be print first. Okay, now this is complete. R. Okay, so now move to the R. So LRP. Okay, no left, no right, print. So E will print. And all completed. Now this step will perform. So B will print. Now all three completed. We will move R first. Okay, so LRP. Now this L to move L side. LRP. No left, no right, print. So F will print. Okay. Now move right. So this LRP. No left, no right, print. G will print. And then all completed. This P. C will print. Now this R completed. Now print A. Okay. So we are getting this order. So this is a post traversal. Here root node will always come at the last. Okay, so in this way you can traverse your tree in any order, in order traversal, pre-order traversal, and post-order traversal. So some question is asked based on this. So like some theory assignment question is also given on this, and your regular assignment weekly. Otherwise, one question is there. Yeah, this one you can see. So here, uh, which of the following order will be printed by the given code snippet? So here one traversal is given, T is given, and algorithm is given. So which algorithm is actually this? This is pre-order, post-order, and in order. So you can see first step is left traversal, second is right traversal, and third step is print statement. So left, right, and print. So this is a post-order traversal. Okay. So you can apply the post-order traversal on this, and you can traverse the node, which we have discussed in previous example in this way. Okay, and you will get the answer for this. So this type you should know traversal. So this traversal actually works for any binary tree. Okay, we can apply this traversal on binary search tree or binary tree, normal binary tree also. Okay.
So there was one question on traversals and binary tree. See, from the post and pre traversals, we can reconstruct the binary search tree. Correct?
Yes, binary search tree. Yeah, correct.
If you have to reconstruct the binary tree, is it possible?
Yeah, binary tree is not possible by single order.
Okay.
So if suppose if you have the order for binary search tree, you can create a tree from the pre-order by the only pre-order or the post-order, but you cannot create the binary tree from in order.
Correct.
Okay.
Yeah.
In pre-order traversal, suppose we have some nodes. Okay. In pre-order traversal, what you can do, you can simply start the creation of binary search tree and select the first node as a root node, and after that take read the element from left to right.
Correct.
And
That's
one by
fine.
one insert this. And post-order traversal, just pick the last node as a root node and traverse the node from right to left, one by one, and insert in the binary search tree. But in order traversal, you cannot figure out the root node.
Correct.
So you cannot recreate the binary tree, binary search tree. Okay.
Correct.
So this is the from binary search tree. But if we have these traversal for binary tree, so we cannot recreate the binary tree again with only one traversal. Okay. So we need at least two combinations. So either in order and pre-order, in order and post-order, or pre-order and post-order.
And how would we go about doing that?
So that let me first create the order, all order for this any tree. Okay. So I'm taking some example. So like a same.
Sir,
Yes.
I have a question. There was one graded assignment where I think pre or post one of the order was given.
Okay.
And as per the
Let's have-
solution, in order was taken as the elements in the ascending order. So even if with one particular order that is given either pre or post, can we do that?
For binary search tree, we can do that, but binary tree we can't do that.
No, it was binary search tree.
Okay, that we can do. So let me open that assignment. So this is
Graded assignment. Yeah.
this is in Week-7 or Week-6. AL tree. I think that is in Week-6. Week-6. I think you're talking about this.
Oh, yes, sir.
So here what is given? Pre-order. Okay, so this is given pre-order. And which one of the following is representing post-order traversal for this binary search tree? So what you can do, you can simply create the binary search tree from this, So you can take this order, and in pre-order, always the first value is the root node. Okay, so just take this as a root node. After read the element one by one from the left to right and insert according to the binary search insertion.
Okay, sir.
So
Okay,
10
got
will
it.
insert here, and then 12 will be insert this side. Okay, and 11 will insert less than, then greater than, then this side. Okay, 20 will insert here, and 18
Yes,
will insert.
yeah, I got the idea, sir. Thank
Okay,
you.
after creating this, just traverse this by the post order traversal.
Post order, yeah, okay.
So,
Okay.
yeah, so if in the question if it is mentioned that the binary search tree is given, then the order doesn't matter, right? Well, whatever traversal they have given, we can construct a binary search tree, and then from there we can get to the
No,
answer,
you
right?
can't create the binary search tree from the in order traversal. Okay, just remember this. You
Oh,
can only create the binary search tree again by the help of pre-order or post-order, not from the in order. Okay,
okay, sir.
in order you cannot recognize the root node, because root node will come in between. Okay, so I'll tell you about the binary tree. I'm not talking about binary search tree now. So binary tree. So let me just create the binary search tree. Sorry, ordering for this tree. So in order I'm writing here. So in order, first we will D will print. So you can apply the all logic, so that this left print are okay in this way. So D will be print first. After that B will print. Okay, and then E will print, and then A will print. Then you will move to this side, and then F will print, C will print, and G will print. Okay, so this is the in order, and pre-order for this tree is, so pre-order is A, then move to left, then B, then move to left, then D, and then E. Okay, then you will move to this side and C, and then F, then G. Okay, so this is the pre-order. Now post order for this is, so that L, R, P, so that means D first, then you will move to E, and then B. Okay, then we'll move to this F, and then G, and then C, then A. Okay, so these are the three order we have. This is the for the binary tree we are talking about now. Now, if we want to create this, recreate this binary tree by this order, now we don't know, we will not follow this thing. Okay, so that if the value is greater, then we will insert to the right or left. We don't know about this. This is the different level. Okay, so how we can create the same binary search tree, binary tree by the order? So we cannot create by any single order. Okay, we know the root node, but we don't know which side that next node will be at in the pre or post things. So in this case, we need the combination either in order and pre order, or maybe in order and post order. So these are the two way where we can directly recreate the as it is our binary search, that binary tree. But we can also create from this pre-order and post-order. But some case we will get some little bit different binary tree by with the help of this pre and post. Okay, so in some place we will get the different, but order will remain same, but tree structure will maybe become little bit change. So, for example, in and pre. So, in order is given and pre order is given. Okay, so in order is given like this. So, D, B, E, A, F, C, G. Okay, and pre order is given A, B, D, E, C, F, G. Okay, we know that pre order have the first node root node. So, you can make simply this root node here. After, what you will do, you will just traverse the node in pre-order traversal, but you will check the position in the in order. Okay, so here when we are selecting A, so we will mark this A. That means which nodes are coming on the left side. So all nodes will coming onto the left side. So this D, B, E will come onto the left side, and F, C, G will come to the right side. Okay, but we have to select the next a child level node. Okay, so how we will select this? So we will traverse next node, so B. Okay, now at this second this child level, this B node will be select. So the D is coming to the left, so that means it will become a left child, and E is coming to the right, this will become a onto the right side. Okay, we are not marking this as a node, we are just putting down on the left side or right side. Okay, now next value is D, so we will, this is single node, we will mark as a node. Now next is E, so this is single, we will mark as a node. Now next is C, so at this level we will select this as a child node of A. Okay, now you can see F is coming to the left, so we will link to the left side, and on this side we will write as a G. Okay, now next node is F, so this will select F, and this is select G. So now you can see the structure, so we are getting the same in this way. So in this way, pre-order and in-order combination, we will traverse the pre-order from left to right one by one, and we will check the position in order, and we will create this tree. And with post order, so in order, so like D, B, E, A, F, C, G. Post order is this D, E, B, F, G, C, A. Okay, now we will just perform the reverse things. Okay, so this is now a root node A, and we will check the position in order. So in order, left elements are coming this side, so D, B, E, we will follow the same order. Okay, we will write in the same order, F, C, G. Now we will traverse from right to left this. So next is C, so we will mark this node as child node at this level, and we will connect F onto the left and this part onto the right. Now next is G, so will this become a node? Next is F, this become a node. At this level, B is coming first, so B will become a child. Okay, so now D, we will move to link to the left, and E will link to the right. Now E become node and D become node. So now we are getting the same binary search tree. And now third is that pre-order and post-order. So here this is little bit tricky. So, but there is a chance you may get it some little bit different binary search tree. So in some case, so like we have this A, B, D, E, C, F, G. Okay, and post order, this is D, E, B, F, G, C, A. Okay, so in this case, so for every node, actually we looks so here we know that this is a root node. Okay, so A. Now for each node, we check which node will come on the left child and which node will come on the right child for this A. So how we will look this? Okay. So some conditions are there. Okay, so A, B. Okay, pre-order, traversal, and right order traversal. Okay, yeah. So here what we will look. So from this A location, okay, and we will check both orders. So pre-order, we will check what is the just right value for this A. Okay, so that is actually we consider as a first we are writing C1 and C2. Okay, C2. So this value we will write as a child one B value B, and what is the just neighbor of this A in the post order from right to left side, just closer C. Okay, this C. If these C1 and C2 value are different, okay, if the C1 and C2 value are different, we will make this first C1 as a left child and we will make this as a right child. Okay, so if this is different, now this is the case here actually. Okay, so we are getting this B here and C here. After that, same things we will check for B. So now B for B, C1 and C2. So just check from B this side, okay, and this side. So what is the just right value for this is D. Okay, so this is D, and just left value for this is E. E. So you can see both are different. So we will make this as a left and this as a right. So this will become D and this is now E. Okay. Now we will check for C. Okay. and we will also mark that which node has actually inserted into our that tree. So that B is now become, and D is also inserted, C, and this B is also inserted. Now D and E. So this is also done, and this is also done. Okay, yeah. So now let's check for the. We don't know which node we need to check. We suppose we try from D. So what are the D node? Okay, so that C1 and C2. But if you see the D, you can see the right value is already become a node. So that means no right, that no node is possible for the D. And same here, you can see the left value. So there is no value for the left. So that means this is the leaf node. So no node is coming below this. So now check from E. Okay, so C1 and C2. So again E. So you are getting mm, uh, huh. Okay. So in this case also E, we are getting C here. Okay. Oh, C is also become. Okay, sorry, I missed this. So E we are getting on the right side. It is also be added into the node. So which we have marked wrong. 1, 2, 3, 4, 5. Okay, 1, 2, 3, 4, 5, and 1. Okay, so this is fine. Yeah. So again, we cannot take C because it is already included, and same here. So D is also already become a node. So that means no node is below this than E. Now we will check for C. So for C, you can see C1 and C2. So from C, you can see F is coming to the this. So this is F, and from C here, so this G is coming. Okay, so G. Now both are different. So make this as a L and this as a R. So this is now F and this is R. Now you can see we are getting the same in this case. But some case, what will happen if suppose this B node only contain this E child, not D. Okay, this not this one. So in this case, what will happen when you will calculate this B child? So B, C1 and C2. Okay. So suppose this D is not there in the tree. So in this case, what will happen? You will get is that in the given order you will get a right value of this B is same E. Okay, and same things you will also get the E. Okay, in this type of situation, at that time you cannot decide that. So here both are same actually. In the same case, that means only one child is connected to this B, but you cannot decided that which side which is connected onto the left or right, that you cannot uh, recover. Okay, so in this case you can connect this E either into the right or maybe left. So this is just a one condition when our tree become a different. Okay, so suppose this is the input tree, but when we are recreating, so maybe you can connect this onto the left. So this is one case where our tree become a different when any node have only single child. So it may be connect into the left or right during the recreation. So this is one drawback in the pre and post that ordering when we are recreating. Otherwise, with in order, pre-order, we will get the same. In order and post order, we will get the same. But pre-order and post order, if this is not the condition in the binary search tree, then you will get the same. Otherwise, there is a chance to get in different structure. Okay, so this is regarding this ordering. Okay, any query in this?
So, sir, for every same occurrence in like the C1 and C2, we would get two different trees.
Yeah, two possibility. Either you can connect onto the left or you can connect into the right.
Okay,
if you are
so
getting both equal.
right. So out of all of the scenario or all the cases, like every time we get a same, and for every same there will be two trees. One of them would be the solution of all the possible trees.
Yeah, all the possibility you will get a one possible solution.
Okay.
Okay, so yeah, this is the way to recreate the binary that binary tree. But binary search tree we can create from any one order, pre-order and post-order, not in order. Just remember this.
Sir, can we cover recursion now? That last question.
Recursion of?
I mean those recursion complexities solving.
Okay, you're talking about that recursion things. Okay. So I'm coming on that. So I have that question also in this document. So let me discuss that first. Okay, so if you want. So here some recurrence relation is given. So this type of recurrence, we will just find out the complexity. So we will solve one by one, and you should know recursion tree method. Okay. So in recursion tree method, we can create a recursion tree for any recurrence relation. So let me take these four and we will generate the recursion tree. Okay. So first thing is this Tn equal to 2T n by 8 plus this things you can write n or okay big O n, both are same things. Okay, suppose we are writing n. Okay, so in this way, this is the main call. Okay, so Tn, this is the first call. After that, you have two recursive call. Okay, so T n by 8 and T n by 8. Okay, so apart from that, this recursive call, what other time is required? Okay, so these are the two recursive call, and apart from that, you need n step. Correct? So that means this level you need n steps from the first call. And when we just expand this more, so now this is now a new input. Okay, for the problem. Just so at the place of n, just put this n by 8 at the all place, just place of n. So in this way, now T n by 8. Okay, so how we can write 2T n by 8 into 8. Okay, 64. So plus n by 8. So this equation will become like this. Okay, where we have replaced all n by 8. So that means we have two call T n by 64 and n by 64. T n by 64. And apart from that, we have additionally n by 8 step. Okay, same things we will get from this side. Okay, so at T n by 64 and T n by 64, and apart from that, we have this n by 8. Okay, now you can expand this in this way some more time, or maybe in 2-3 steps you can understand the order. Okay, so just expand 2-3 level, and then you can figure out that your number of steps in each levels are actually remains same, or it increases or it decreases. So in this way, so number of steps, not we are not counting the call, we are just finding out the steps that number times which are required apart from the recursive call. So at this level you can see n plus 8 and n plus 8. So that means 2 times that 2 into n divided by 8. Okay, so this is now n by 4. Okay, so you can see total number of steps at this level is n by 4. In the previous was this n. Now next level, you have
So
4
what
calls.
you applied any geometry progression? How did you come to this one? This number 2 into n by 8.
No, this is the actually when we call this function, we have written this expression. Okay, so this expression completely. Correct?
Correct.
So how many steps, additional steps are required apart from the call? So this is actually a call, recursive call. Okay, recursive call time. But these steps are required additionally. So this is the time required, and this is recursive calls. Okay, so what time is required for this call, and this is n by 8, and same we have the this recursive. So for same we have this.
Twice,
Okay.
we instead of n, we have n by 8 in both places.
So we have added both n by 8 2 times. Okay, so we are getting this 2 into n by 8, n by 4. In next step, this will expand 2 times. Okay, so that means T n by 64 into 8. Okay, so 8 into 64, like this. Okay, and again plus another call, same, and 8 into 64. And apart from that, we have this input, so this will remain n by 64. Okay, now we have expand this. We have just replaced n by 64. So just put this in the all place. You will get this as the additional time for one call. Same for this, same for this, and same for this 4 times. Okay, so that means 1, 2, that 1 and 2 and 3 and 4. So 4 times you are getting this n by 64. So total time of this level is 4 into n by 64. So you will get 16 n by 16. So in each level you can see here this is total steps are n, here n by 4. Okay, so now it is divided by some certain that constant. Okay, and this constant is increasing at every level. Okay, this is now 2 square, this is now 2 to the power 4. In this way it will increase. So you can see the number of operation at each levels are decreasing. Okay, so you can figure out these things if your number of total operation at each levels are increasing, decreasing, or are same, and based on that you can decide the complexity. If it is decreasing, at that time you can simply write the complexity same, this order of this is actually called as a fn. Okay, this part called as a this fn. Okay, and so you can write the same complexity for this time. So the complexity of this expression will be big of n, same as it is. Okay, if your time is decreasing. So this is the one decreasing method. Okay, and another condition is like if value is same. So like second expression. So 4 t n by 4. So t n equal to 4 t n by 4. Okay, n plus n or big O of n. Okay, so we can write like this, so tn, and this time we have 4 call. Okay, so we have 4 call, and every time we are just calling this t n by 4, t n by 4, t n by 4, and t n by 4. Okay, apart from that we have time plus n. So total additional time is required n at this level. After that, this will again have a 4 call. Okay, that will be t n by 16, like this. Okay, 4 times and plus that n by 4 at this level. Okay, so this is the input. This will come as the same here, and same 4 call, and last additional time is n by 4. So same 4 call and additional time is n by 4. Same 4 call and additional time is n by 4. Okay, so that means 4 times you are getting this n by 4 at this level. So total time is 4 into n by 4, again n. Okay, next level you will get 4 times. Okay, so now this time 4 call and n by 16. Okay, but you have total 4 call this time. Okay, so you will get for all. So that means 4 times this and for this part. Okay, and 4 times n into n by 16 for this part, and same for here, same for here. So total 16 times you will get this n by 16 at this level, and 16 into n by 16. So again n. Okay, and in this way, if you are getting this behavior, so if your total number of operation remains same at each level, so at that time you can represent the complexity fn log n. So fn is the direct this value, and so and log n. This will be the complexity. Okay, so this is the another condition, and check if you're getting that increasing things. I think this is not that one. So okay, but still we will understand the that behavior for this recurrence. So t n equal to t n minus 1 plus this is n. Okay, so this recursive recurrence actually work like as a that selection sort or insertion sort behavior. So that means we have Tn, we need we have a call Tn minus 1, but additional time is n. So that n. Okay, now this is the input. So next call will be Tn minus 2. Okay, and this will be passed as is here. So n minus 1. This is n minus 1. Now next, only single call is there every time. So every time we will reduce 1, 3, and this is the n minus 2. So this is n minus 2. So in this way, every time we are reducing 1. So total n levels are required. Okay, n levels are required to reach at the T1. Okay, and every time we are getting this step. So n plus n minus 1 plus n minus 2 plus n minus 3 till 1. So this series we got this addition n into n plus 1 by 2, and this is the n square complexity, big O of n square. Okay, and the last one is Tn by 2, and this is actually related to the binary search tree. Tn by 2 and plus 1. So in this case, this is Tn, and now we have Tn by 2, and we have 1 steps. Okay, this is constant. So plus 1, that means overall 1. Next step, so this 1 is not dependent on the input. This is fixed constant. So that is next is Tn by 4 plus 1. So same 1. Okay, Tn by 8 plus 1 in this way. Okay, so 1. Now at this level, every time we are dividing the input by 2, so you will reach at the 1 in log n steps. Okay, so in this case, log n, every time you have log n labels you have, and each label you have 1 operation. So 1 into log n. So total is log n for this. But in this case, we have figured out the previous 2 cases when our complexity decreases and remains same. But some time we will get the when our complexity is actually increases. So this is okay. This is also example of decreasing. Here 1 recursive call we have n by 2. Okay, this is also not 2t. This is a n log n complexity. This is the example. Okay, so like this type of recurrence. So Tn, you have 4 times call. Okay, so 4 times call. Every time you have Tn by 2. Okay, Tn by 2, Tn by 2, and Tn by 2, and plus n. So this level is n, but next level you can see 4 times call and plus n by 2 for this part. Okay, then 4 time call, then plus n by 2, then 4 time call and plus n by 2, and 4 time call and plus n by 2. So 4 times you are getting 4 times n by 2. Now total is 2n. Okay, next time it become a 4, then 4, then 4, then 4. Okay, and this is n by 4 actually. Okay, we are dividing by 2, so it become n by 4. So 16 times n by 4. This is 4n. Okay, so in this case you can see it is increasing by some factor. Okay, so in this case we calculate the complexity by this formula. So let me just show you that one second, week 8. Yeah, this you can see decreasing simply fn equal fn into log n, but increasing we take this big O n to the power log base cr. So we use this formula. So big O n to the power log base c and r value. So what is this r and c? So this r is just a number of recursive call. Okay, so how many times we are calling every time? Okay, so this is 4 times. So this is called as a r value, and this division value is called as a c value. Okay, and this is actually a fn. So just put this value here. So this is n log c value is 2 and this is 4. So 4 we can write as a 2 to the power 2. Okay. Now this 2 will come at this place. So n into 2 to the power log base to 2. This is now become 1. So big O. Sorry. 1 second. Okay. So any query in this recurrence that recurrence relation?
No, sir.
Okay, so I have discussed all three category. So just expand the recursion tree at 2-3 level and figure out that order actually it is increasing or it is decreasing or it is constant. And based on that, just choose the condition. So you can solve.
Will you share this PDF?
Which PDF?
The one which you're just showing right
now. This we are using as a one notepad. But
the one with the questions.
Okay, this question one.
Yes.
Okay, okay. So let me just check the drive. Okay, so I'm sharing the chat now. Okay. Okay, so that will be done. We can share experiment review. Okay. So this is the same slide we have. So this is just a set of some questions of the previous terms. Send in the chat. Okay. So yeah. So this is about the recurrence tree. But in BCAD, what you can focus more? So in BCAD, you can focus more in this number of inversions. Actually, this question is also important. Okay, from BCAD. So number of inversion you can simply calculate for the some simple list is given. Just compare with the sorted order. So 1, 2, 3, 5, 6, and just check which pair you are not finding at the correct place. Or you can also simply check. Just check for the each value after this value which are the smaller value, so that will become a one inversion pair. So you can see one, this is the one and no lesser value than this, so this is not creating the inversion with anyone. Now from 4, just read the value after that. So 3 is creating one inversion pair with this and 2 is creating one inversion. Okay, because 3 and 2 are the smaller than 4, but it is coming after that. So with 2 we are getting 2 inversion pair, and from 3 on the right side one smaller value is there. Okay, so it is creating one inversion pair, and from 6 2 smaller value are there on the right side, so it is creating 2 inversion pair. Okay, and from 2 this is okay and this 5 is okay. So that means we have total 5 inversion pair in this. And what are these inversion pairs? So that is actually 4 3 and 4 2, and with 3 actually 3 comma 2, and with 6 is 6 comma 2 and 6 comma 5. Okay, so in each pair you can see the second value is smaller than this. So this is one important question from week 8. So you should know number of inversion, how we calculate this. Sometimes list size is given, what are the minimum number of inversion pair, what are the maximum number of inversion pair. That type of question is also asked. Okay, so you can directly use the formula. So minimum number of inversion pair is 0 if list is already in sorted order, but maximum number of inversion pair you can find out that by the formula n into n plus 1 by 2, like this. So some direct formula we have for this. Week-7.
I think n into n minus 1 by 2, right?
I think n into, let me check this. Just here. This one, sorry. n into n minus 1 by 2, not plus. So just use this formula to direct find out the maximum number of inversion pair. Minimum is 0 and maximum is this. Okay, so otherwise for simple small list you can manually check okay number of inversion pairs. So this is one important question from week 8. And apart from that, regarding this MOM, yeah, MOM related some questions. So that is one is given in the mock questions. So some code is given that this one. So I hope you all know that how it is solved. Actually, this mock unit Quiz-2. This one, okay. So mom code is given and this sequence is given. So how the median will be returned by this function. So here you can simply use the dry run, or you can simply, if you know the concept of MOM, you can directly apply the things okay, without checking the code. So here we are taking the block of 7 elements. So just also note down these things, how many elements we are using as a block. So sometimes we use as a 5 most in our algorithm, but if this is given as a 7, so select as a 7. So that means what is the way to solve is just take first 7 element and sort them element. Okay. Then again take the next 7 element and sort that. Then again take the 7 element and sort them. So in this way, all just sort all the block of 7 element. After that, take the all median element of this block. Okay. And after taking the median element of the all blocks, again sort them medians element. Okay. And then select the middle element. So that will be the median of all medians. So in this way you can solve this. So this is one very repeatedly question from the week 8, and one is this inversion pair. So you can see this size is given directly. You can use the formula, and sometimes this okay. So this type of questions like this quick select and this. Okay, so you should know what are the recurrence relation of quick that fast select using MOM. We can say. Okay, so first we have the normal find the kth smallest and kth largest. Okay, so that is called as a quick select. So what is the drawback for that is actually in worst case that takes order of n square, similar to your quick sort. Okay, if our pivot element is always coming at the corner side, so it will take as a worst case time order of big of n square. So quick select also take this time in the worst case. But that fast select using MOM. Okay, so when we are using this MOM to find out the median elements, so this worst case situation converted into a that average or best case kind of situation. So that means our pivot element will not come into the uh, corner case. So that is sure. So it will actually reduce our time to big of n for quick select, fast select. Sorry.
So what is the best or average case for quick select?
Best is order of that n. Okay.
Without MOM.
Without MOM, you can select that in order of n, and that or best order of n, yeah, and worst is order of n square.
No,
For
O
quick
of n
select.
square is okay. So average is not n log n, it is O of n.
O of n. Here we are selecting the element. We are not sorting the element. Okay. So
No,
what
no,
we
I
are
get it.
doing?
Yeah.
Yeah. So this is not n log n this time, because every
Okay.
time we will discard the part. Okay. So here our recurrence relation will become like this. So Tn equal to, and next is the just one recursive call, and either on the left half or on the right half. So that will become a n by 2, Tn by 2. Okay. And now it is taking the time n. This is for partition method. Okay. But in quick select, this finding the kth smallest largest smallest, we call only one time on the recursive, not 2 times. So because of that, this become a recursion tree like this. So Tn is there. Then next call is Tn by 2. Okay, so first time this is n. Now next time this will become a the Tn by 4, and now plus that n by 2. Okay, so
So
next time it is reducing.
n plus log n in the end. So n is the dominant one. So it becomes O of n.
No, what you said, n log n.
So this t of n by 2 plus n will reduce to n plus log n. And since n is the dominant component, so it becomes O of n.
No, no, no. We are not saying this. Here we are following that. You can see at each level our total time is decreasing.
Okay.
Okay, so this is just a case of decreasing method. Yeah, this total steps will move to the log n times.
Yeah, so it will become n plus log n.
No, it is
And
not a
that,
n log n. This is not a n log n.
no, n plus, there's an n on the right hand
Haha,
side.
n plus log n you can say.
And then that will reduce to log O of n because n is a dominant
Yes,
component.
yes, yes. You can say this. Yeah.
Okay.
Otherwise, if you are talking about the recursion tree method, so you can see the number of operation at each level are decreasing at every time. So this is n by 4 next time. So in that case, we always pick the complexity this fn. Okay, so order of n we are getting. Okay, but in the case, so this is the recurrence for that best case, and this is the same recurrence for the fast select using MOM. Okay, and best case for quick select without MOM.
So
But
this is best and average for quick select is both O of n. Worst case is n square. And for fast select, everything is O of n.
yes, OFN, correct. Okay.
All right, sir.
Yeah, quick select that worst case is recursion relation is Tn equal to Tn minus 1 plus n. Okay, so this is now a recursion because every time we will call on the n minus 1 element if our pivot is coming at the corner. Because of that, it becomes
I was just confused as to whether the average case of quick select is also n log n or not. So now I've learned that it is O of n. Worst case is O of n square, and fast select, both of them are O of n.
O of n, yeah. So same things, we can also improve the quick sort actually with the help of this MOM. Okay, so you know that in the normal quick sort it takes worst case order of n square, but if we use this MOM, so it will reduce to the same n log n.
N log n. Right, sir. Thank you.
Yeah. So just these type of questions from BK. Now this is again inversion pair. We have sent that. Yeah. So regarding from Week-7, so we have discussed this AVL part. So you can see here some sort sequence is given, and the leaf elements are asking. So just create the AVL tree for this and find out which elements are coming on the leaf node. So you should know the creation of AVL tree. Some properties we have already seen many times in the previous question. So this related to the AVL tree, you can see.
So I've seen in some PYQs there are some lengthy from Week-8 there are some lengthy code snippets, probably about a page long, that are given.
In
So can
weekly
we
assignment, you are saying?
No, sir. In PYQs also. So in previous years, I've seen like 2 questions at the end generally used to be like long code.
Okay.
So that is not, yeah.
So generally, that type of question asked him from the Week-9, where some dynamic code is given, dynamic programming related code is given, some sort code, and you need to figure out that what type of algorithm is used, okay, and some basic things, what the code is doing. Yeah, some type of question will maybe come in the interim exam related to the Week-9 content, or sometimes
Not
Week-8
in this
also.
Quiz-2.
Quiz-2, I think no. So generally we not give a long code based question, but yeah, some 1-2 question you may expect in the interim exam.
Got it, sir. Thank you.
But that question will be based on that. Some code will be given, and what type of algorithm techniques is used, what is the complexity of the code, like this. So that code will be based on either divide and conquer approach or maybe dynamic programming approach, like this. Only 2 methods.
Okay, sir.
Okay. So yeah, this Week-7, another topics, Huffman codes. Yeah, we have discussed this prefix and postfix things. This type of question is also repeated many times. So some sequence is given. You know that interval scheduling, we sorted the activity based on the starting time or end time. End time. Okay, deadline question we have already done. This type of question, this is also based on that how many minimum number of rooms are required. So you can also solve this by the manually. Okay, so this is just a chronological order. You can just take the room and just take that if it is busy or not. This can be solved manually. Open codes creation, you know that how You can create the Huffman codes with the frequency. Yeah, this I have discussed. This sequence is given. Create the binary search tree. So okay, this is very important. Uh, and AVL tree. Yeah. So only these types of questions you can expect. Yeah, this you can see. This question is actually tricky. So here it is asking that what are the valid codes actually. So here you can validate the prefix property. Okay. So just check that this 11 is coming at the prefix on any code. No. 10 is coming on any that code. Yeah. No. So 01 you can see it is coming. So this is not a valid code. Okay. So same things you can check in the every code and you can figure out which one is the valid or invalid. So prefix rule you can check here. So like this is you have already seen, just sort this activity based on the end time and perform. This is interval scheduling. So this type of person you will find out from week 7 and 8. So if I think if you have any specific query, then you can ask to discuss. Okay, or any other question you want to discuss if you have any doubt. Anupam, I think you have some post on the discourse I've seen just before the session.
Yes, sir. So I had put one post for discussing how you can find the kth smallest element using max heap.
Okay.
So I was confused as to whether that approach is even possible or not, and if it is possible, what is the time complexity?
So
So
using the max heap, how you can find out that? What you have to do, you have to make the first max heap from the n element. Okay, so that
not
means
from
first.
not from n element, sir. So the question that you had given is the question that was posted was that there is a list of n elements. Can you find the smallest kth smallest element using a max heap of k elements only?
Let me check your. One second, this one, no?
Yes, sir.
Okay. So which of the following statement is true for searching the kth smallest element in the unsorted array of n, which all elements are distinct? Okay. So some methods are given. So which strategy will work in this complexity or not? So
So
using a max
second
heap
one
of
is
size k. Yeah.
yeah,
So
yeah.
using a max heap of size k. Okay. The max heap we are talking about max heap. Okay. The worst case running time will be the order of k. But here the question is.
First question, sir, is can you even do it using max heap of size k? When you have n elements, how can you find the kth smallest element using a max heap of size k? That was the question number one. And then the complexity of that was question number two, which I've written on top. If you read that.
Okay. So what you can do, yeah, we can find out that, but we cannot find out use in the complexity of big O of k. Okay, so suppose we create the kth. We can take any random element of that k element from the n. Okay, and we can make the max heap for that. Okay, so first maximum element out of k element will come at the top. We can remove this. Okay.
So we keep
Again
on
we will
removing it. Yeah.
again. So first element we will remove that, and again we will take one element from the next an element, and we will create again max heap. So in this way, in the after completion of the all process, you will get a that 7 smallest element, that k minus 1 smallest element in at the left actually.
Got it, sir. So basically, what you do is you pick up a random set of k elements first, create a heap from that, then keep on removing the max element from there and keep on replacing it with smaller elements
So
from
that
the
type of
end
things.
list.
Yeah.
And at
So
the
what?
end, the max, the root element will become the answer.
Yeah, correct. So
Okay,
in
so
this
that will
way, you are
be
trying to do, yeah.
yeah. So I guess that will be n square.
Not n square, because every time so we have the max heap of k actually. Okay, And when we are inserting a new node into this, so that will take log k time to insert it, again recreate the max heap. So it will take, actually we are traversing all n element, and each time we are inserting one element into this, so it will take log k time.
Okay.
So n into log k.
N log k. Okay, sir.
Okay.
Got it, sir.
Yeah. So in this way we can do this, and you can try to write the code using this. So that is one problem actually. So you can try to find out that. I think some question is given in some place, maybe in assignment. I'm not sure. The same question is there, but yeah, still you can try to solve this type of problem by the code. Okay.
Got it, sir. Yeah. Thank you, sir.
Okay. Any other query? Others? Any doubt?
So the Huffman code question that was there in the slides that you've shared.
Okay. So this one?
Yes, sir.
Okay.
So in this, we need to check whether any of these, do we create a tree and then check
Not need to create the tree. Here you can just validate this code with the help of first thing, one more condition you can check here, how many elements we have: A, B, C, D, E, F, 6 elements. Okay. So code length cannot be the more than 5. Okay. So that means if we are creating this any event tree from this, so it may be create like this. So A, B, okay, like this, and then we are creating C, suppose, and then we are creating D, okay, then we are creating F, E, and then we are creating F, okay, like this. So this is the maximum possibility of the code. So at 1, 2, 3, 4, 5. So for 6 elements, the maximum code length will be the 5 digit, okay, 5 digit. But this is the one things, if any code is more than 5 for this, so that is actually not possible. But in this case, you can see there is no code which is like this length. But how we can validate this? So you can simply check the prefix property in this. So this question is only checking the prefix property. So just check the smaller code, and it is coming into the any bigger code as a prefix or not. Okay. So if any code is coming as a prefix, that means that is not a valid code. So you can see this example. This 0, 1 is coming as here. Okay. So this is not a valid. So same things you can check in the another code. So like in this, we cannot see any revision. Okay. So 1, 0 is also not coming. 0, 1 is also not coming. So this is valid. So in this also, so 0, 0, 0 or any code, if you can see, is repeating. So 1, 0, 1, yeah, you can see 1, 0, 1 and 1, 0, 1. You can see this is coming here. This is not a valid. And lower one is okay. So 1, 0 is not coming. Yeah. So lower one is also correct. No is prefix. So you can validate this prefix property, and you can give the answer.
Okay, sir.
Okay. Okay. Any other query? Okay, so if there's no query, then we can close the session. You can post on the forum also if you are finding any other query later. Okay, I think Saturday our TA will also discuss some another PYQs in the next session, that you can join that also. So, okay.
Thank you, sir. Thank you so much.
Okay, yeah, welcome. Okay,
Thank you, sir.
Yeah,
Thank you,
and all the best.
Thank you, sir.